Hey folks, thanks for getting to work right away. We're going to set up our notes as usual. Today we're trying to figure out if a function is linear or nonlinear. That's what we're going to call it, linear or nonlinear. That's all we have to worry about. There are other classifications for nonlinear functions, but we're not going to worry about that vocabulary today. You're just going to say if it's linear or not. And so what's the deal? If a function is linear, the exponents on all the variables are just going to be a 1. Okay. So you can see this guy right here, the variable on that x is a 3. So that is not linear. I'm going to put it over here and I'm going to enlarge that a little bit because I want to say one other thing about it. Sometimes people think, well, what is the exponent on the y? Well, the exponent on the y is a 1. You don't have to write it as a 1. It's just understood in mathematics that it's y to the first power. Okay. So when you don't see a variable or an exponent on a variable, it's a 1. So when we look at this next one right here, let me move that guy down into the appropriate place and let's enlarge it. Okay. So why is this one linear? Well, you can see the f of x is really representing y. So they're trying to trick us a little bit there. You could rewrite this function. Let's move this table out of the way. You could rewrite that function as y equals, and then you could divide the 3 into the 6. Not that that's necessary, but it might make it a little bit more obvious for us. So we get 2x, and then we could divide the 3 into the 5, and that would be like 1.6 repeating. So I'm just going to leave it as a fraction, 5/3, right? Well, where are the variables? Well, here's the variable right here, y to the first power. Here's the variable here, x to the first power. This is definitely a linear function, right? So let's just stop for a second. Let's open up Desmos, and if you would with me, do that. Okay, so I'm doing that right now. And what I'm going to try to do is I'm going to try to graph this function right there. Let's just take a look and see what it looks like. So if I could put y or f of x, it doesn't matter. I'm going to put f of x because I'm guessing people are a little uncomfortable with that. And then I'm going to go 2x minus 5/3. Okay. So I have my function in there. Let's maximize this thing. You can see it's a nice straight line, right? I could put 2x to the first power. That's not going to impact things. So let's see here. Shift 6 gets me up in the exponent. I hit a 1, right? I could rewrite this guy as y because the computer understands that's the same thing. So I hope I'm making this clear. This is a linear function. You can see, boom, right? Now, let's make a table of these values. So let's go here, let's make a table, and I don't know, let's start at 0 and 1, 2, 3, and if I just keep hitting enter, it'll put some more numbers down. Now, the nice thing about having f of x here, if I do f of x sub 1, it's going to stick all these numbers into the function if I tell it, hey, this is my f of x function. Oops. I got to close my parenthesis down. So now what do we have going on here? Ooh, okay. So this is a little bit difficult to see. How much is it increasing by from here to here? It's increasing by 2. Then it's increasing by 2. Then it's increasing by 2. Increasing by 2. Increasing by 2. So if it increases the same amount in the y, and you got to pay attention to the x too. Is the x increasing by the same amount? We went up by 1, up by 1, up by 1. So the y is increasing by the same amount each time. That means the slope is a constant, right? So if we have a constant slope, we're going to have a line over here. So looking at a table, we can also determine if something is linear or not. Let's take the table, for example, right here. All right. So let's move that table out where we can see it. All right, here we go. Okay, so the x is increasing by 1, increasing by 1. So the run, this is called the run, right? The x, the change in x. So I'm going up by 1, up by 1, up by 1. What's the rise? Oh, man, that's a little hard to tell right there. That's what, 34? Going up by 34? How much is this one going up by? Ooh, that's a little difficult to tell. 34 again, right? How much is it going up by? Oh, another 34. Now it went up by 34 again. So the slope would be 34. This is a constantly increasing function. And so I'm going to put it over here in the linear column. Now that's a little weird. Our definition was a function is linear if all the exponents are 1, but I don't see an algebraic equation here, but I can still determine if it's linear or not. All right. Hey, let's take an easy one. Definitely a line, right? All right. So there we go. Right. So maybe we need to add some stuff to our definition up here. Let's come up here and say, let's see if it'll let me write in here. if the graph is a straight line, comma, or maybe semicolon, I don't know. All the points are on the same line. Okay, I just maybe saying the same thing there. All right, so let's look at one that's a little tricky here. I'm going to grab this guy. Okay, now this kind of looks like, there's a straight line there, there's a straight line there, but not all the points are on the same line. Like, well, if you're in art, you call this a line right here, but really in mathematics, our lines are going to go straight forever. Okay, so that's what it means to be linear. Are these points down here on that line? No, they're not. So I'm moving this guy right here into the nonlinear category. I know that's a little weird. Let's do an easier one. Okay, here we go. This one's definitely nonlinear, right? See how curvy it is? The slope is not the same at all places. So as I come down here, negative slope, then I change to a zero slope, and then it goes positive slope, right? So that's a little calculus right there that I just gave you. Here, this one's easy. That one's definitely a line, right? So let's talk about one last thing, and I need you to add it to this column over here. Intercepts. Okay. Usually we say there are x-intercepts, I'll abbreviate it, and y-intercepts. Okay. And let's highlight a few here. Okay. So I'm going to grab the red pen to highlight my intercepts. All right. So here's one, right? Okay. I'll take red. Come on. That's give me a little hassle. So here we go. Here is an x-intercept right there. Here is a y-intercept right there. Here is a y-intercept right there. It's where it hits the y-axis. That's called our y-intercept, right? This is our x-intercept over here. Now let's talk about what is this point right here. It is 1, 2, 3, 4, 5 back. So you go -5. X is always coming first, right? And then our y value is 0 because we're on the x-axis. Over here, I'm not going left or right at all. So my point here would be 0. The x is going not at all left or right, but the y is going up 1, 2. So that's our y-intercept. So on this one, let's label it here. X-intercept equals -5, 0. And y-intercept equals 0, 2. Now, do nonlinear functions have x and y intercepts? You bet they do. Here it is. Here's an x-intercept. This one has 2 x-intercepts, right? So a linear function is only going to have 1 x-intercept. Nonlinear functions could have lots of x-intercepts. So this one has 2 x-intercepts. That was 1, 2, 3, 4. So that's -4, 0. So let's label that. That's our x-intercept. Up here we had this one right here is our y-intercept. That's what they're going to ask us about in the homework. Okay, 1, 2, 3 x-intercepts. This is not a one-to-one function because there's 3 repeated values that have zeros. Okay, for their x-intercepts there. Here's our y-intercept, right? So that's what we're doing in our homework today. We're trying to determine if something's linear or nonlinear, and then we're going to determine what the x and y-intercepts are. Thanks for watching the video. I hope you got some notes. I hope I made that clear.